So we're going to start today's lesson about looking at vectors in component form. So expressing vectors in component form is almost like expressing it in a coordinate geometry form, except instead of writing it horizontally, we're going to look at writing it vertically. So we're going to start with the Cartesian plane. And then I'm going to label, let's do 4 and 3. And let's make this vector v, for example. So here, instead of writing coordinates such as 4 and 3, I can actually write this in component form, which will be 4, our x value on the top, and 3 on the bottom, which is our y value. So that's what we can see down here, highlighted in yellow. So here we can write it in component form by putting it vertically where x is on the top and y is on the bottom. You'll also see it expressed into component vectors. So also think about it as if I had unit vectors, let's say I had the unit vector I and I had a vector, let's just call it j. And let's just say vector I and vector j are worth 1 unit. Can you see that I would need 4 of these vector i's and 3 of these vector j's? So another way that we can write this is that 4, 3 can also be written as 4i plus 3j. So notice here, by treating vector I and vector j as unit vectors, can you see that I have 4 lots of vector I plus 3 lots of vector j? So these are the two ways that we can write our vectors in a different form than what we have been doing before. So the key takeaways is that the x value is the x component of v. Similarly, the y value is the y component of v. We also sometimes call component form as column vector form, and we call when we're listed horizontally as Cartesian form. So for example, let's look at question 1, and we want to draw our first vector, which is vector 1, and it's 7, 6. So I'm going to go to the Cartesian plane. I'm at 7 and I'm at 6, and I'm going to draw my vector from the origin to that point there, and we'll call this vector 1. And remembering these, assume that you're starting from the origin. Looking at vector 2, notice that I'm at -5 and I'm at -7. So my unit vector, my vector 2 is going to be here. If I look at vector 3, it's a little bit different. So notice I have an x component, but I don't have a y component. What that means is that I'm going to go along the x-axis. I'm at -6, but notice that my vector doesn't move upwards or downwards. So it's simply going to be a horizontal line. So that's going to be my vector 3. Similarly, for vector 4, I'm going to have just a vertical line. So I don't have any x component, but I do have a y component that goes all the way down to -4. Now again, if I were to also write this in terms of vector I and vector j, so if we look at vector 1, for example, instead of writing 7, 6, I could also write this as 7 vector I plus 6 vector j. Also, for example, if I wanted, let's just say vector 3, where I don't have a y component, then that would simply be written as -6 vector I plus 0 vector j, or -6 vector I. So the next thing we're going to look at is something called scalar multiplication. So think of a scalar as like a quantity. So here we're multiplying by a scalar quantity, and we multiply each component by a certain constant. So think of this value here as some sort of constant. Think about it here that, for example, when I'm multiplying in column vector form, so for example, if I have the column vector 2 and 3, if I'm multiplying by another number, let's just say 4, what I can do is that 4 can be multiplied all the way through the column vector. So that way I would end up with 8 and 12. So here, looking at my example down below, what the question's asking for is that we're given vector v and we want to draw a vector where the scalar multiplication is -2 and another instance where the scalar multiplication is 0.5. So here what that would mean is that essentially I have my scalar of -2 out the front of vector 2 and 1. So if I were to multiply that scalar through, I would end up with -2 times 2 and -2 times 1. So I'm thinking about a vector that has a run of -4. So let's just say maybe my starting point is here. So I'm going to go to the left by 4. 1, 2, 3, 1, 2, 3, 4. And I'm going to go down by 2. 1, 2. So notice here, this will be our vector. We'll call it vector A because it's question A. The next one we're going to look at is for B. So here, our scalar is going to be 0.5, 4, 2, 1. So half of 2 will be 1 and half of 1 will be a half. So here what that would look like is that I have a run of 1 and I go up by a half. I know that it's really small in the diagram here, but again, can you see that all of these scalars, they're all also parallel to each other? Can you see that irrespective of their original starting point, notice that they are still parallel to one another. The only difference between them is their scalar. So that brings us to question 3. So if I want to determine if two vectors are parallel, then what I can do is I can use scalar multiplication to help me. So here, if I want to find y, notice that I have that this vector 4, 3 has been multiplied by some scalar and it's given us another vector of 8y. And we know that they're equal because they're going to be parallel to each other. So here, if I think about just my y components, so let's think about 4 and 8. Notice here that I have the scalar multiplied by 4 is going to equal 8. So my scalar multiplication will be 2. So here, 2 outside of 4, 3 will give me 8 and 6. So therefore, y will be equal to 6. My last part here is I'm looking at adding and subtracting vectors. The good thing about adding them and subtracting them algebraically is I'm essentially adding all the x components together and then all the y components together, and very similar when I'm subtracting. And this works the same way for example 4. I can add all the I vectors together and I can add all the j vectors together. So here, if vector u is equal to this and v vector is equal to this, I want to be able to add the two components. So if I were to add them, I'm going to add 2 plus this 2. So looking at the coefficients of vector I, plus, and I'm looking at the coefficients of vector j. And notice what I end up with is 5i plus 2j. Now, with 5, for example, be really careful. My advice is that if you're not 100%, a good idea is to sketch this out. So let's just say I have a Cartesian plane and I've got x and I've got y. And let's just say I'm going to start by drawing the vector OP. So O and P. And you can see here that I'm at 2 and 2. If I go to look at OQ, notice I'm at 3 and -1, so probably around here. And notice that vector PQ, I start at P and then I'm going to Q. Now, here it can be tempting to think, well, if I want to find what vector P to Q is, you might think, oh, I'll just add P and add Q. However, if I think about our addition and subtraction laws, recall that if the two heads meet, that's the vector I start with, and then I subtract the vector at its tail. So here, vector PQ is actually equal to vector OQ minus vector OP. p. So here I end up with 3 minus 1 minus 2, 2. So if I find vector PQ, it will end up being 1 and negative 3. Alternatively, another way to think about this is if I use the addition rule. Notice that if I follow my vectors, can you see OP plus PQ? That will give me vector OQ. And if I rearrange that, can you see I end up with OQ minus OP. So that's how I can also work that out. Lastly, I'm going to look at example 6. So I have 3 vectors. So I want to find the value of y, which is in vector C, given that C is parallel to A plus B. So here I'm going to start with adding vector A and adding vector B. So I'll have 1 minus 1 plus 2, 3. So the addition of those vectors will give me 3 and 2. Finally, if I know they're parallel, I know there is a scalar multiplication. So I know here that this vector 3, 2 is multiplied by some scalar will give me vector 9y. And just by looking at the x components, I know that my scalar multiplied by 3 will give me 9. So therefore, my scalar multiplier must be 3. So here, to find out my y value, my y will be equal to 2 times 3, which will be 6.